Here we are, we've made it to the final lab of the semester. It's an amazing feeling, and in this lab we get to study some of my favorite physiological processes. We're going to be studying muscle function. And for the sake of this lab, just to start out with, we need to talk about kind of the major types of muscle contractions, or kind of a division between types of muscle contraction. And that is isotonic versus isometric muscle contractions. So they're divided up based on whether they're accompanied by a shortening of the muscle as it contracts. So an isometric contraction, what we can think of is, we'll just think of the muscles in my forearm here. And right now, all of your muscles are always under some level of tension. If they weren't, my hand would be flopping down on the table. Right, so this muscle is actually currently contracted, and it's at a specific length to hold my hand in the position that it's in. So now, as I'm holding it here, I can add increasing amounts of weight, and to keep my hand in the same position as I add increasing amounts of weight, I'm going to be contracting and recruiting more muscle groups to retain that. But this would all be an example of isometric contractions because I am not changing the length of the muscle that's involved, that I'm just generating more force. And so then that contrasts with an isotonic contraction, and during an isotonic contraction, the amount of force that's generated is consistent, and the length of the muscle changes in response to that contraction. So here I'm engaging in an isotonic contraction. There's an initial phase that's isometric where I'm overcoming the forces needed to start movement, and then as my hand moves, the force that's produced is consistent across that range of motion. And so most of our motions consist of a combination of isotonic and isokinetic elements. But for today's lab prep, we're going to be focused on studying just isometric contractions of the frog gastrocnemius muscle. So the gastrocnemius muscle is this muscle here in the back of your calf. So it's a muscle that's involved in moving around. And in the frog, it's just a particularly large, convenient muscle to study. It's supplied by a nerve that runs down the leg, a really large nerve that branches off in the lower back and then runs down and feeds most of the muscles in the leg. That nerve is the sciatic nerve. And so just because of its properties, it's a particularly convenient one to study. So I'm actually going to put in a video that walks through a dissection process for dissecting out and preparing the muscle and the nerve for this lab. So that's going to go in here. Okay, so here's a video of frog dissection, just showing you the tools involved. Here's our frog put on its stomach, so the dorsal surface is exposed, and the frog's being rinsed with a saline solution. Right here, the biologist doing this dissection is using some of those toothed forceps, because that's a little easier for grabbing onto the skin. And the first thing they're going to do is they're going to cut away some of the skin. I'm going to be giving each group just one leg, so I'll do some of this initial preparation for you. And here's Emma to help us. So now what they're doing is just moving some of the skin away from the leg, and what they're preparing to do is you can deglove the leg by basically pulling all of the skin down and even all the way off of the foot. So again, those jawed forceps are very handy. So again, the gastrocnemius here is going to be in the lower part of the leg right here, above the foot. So this is the upper leg where the quadriceps is located. So once again, onto its back. And the frog's hip structure is a little bit different from ours. It has a set of hip bones called the urostyle. So there are two bones that are out to either side, plus a central bone as well. And the sciatic nerve originates at the top of this. So now notice here, right now, this is a set of, they're not cutting scissors, but they're clamps, clamp scissors. And rather than trying to cut the muscle, what this biologist is doing is using these tools to separate the muscle, because the sciatic nerve is going to run from the urostyle across the hip, and it's deep within the tissue of the thigh. So they're separating out the muscle to reveal where the sciatic nerve is located. One note, when you're handling nerves, you don't want to handle nerves with metal implements. So the other thing that this biologist is going to try to do is avoid touching the nerve with these metal implements. And we're going to reach a point where we'll tie a ligature or a knot in the nerve to aid in handling it. And for doing that, we'll just use a piece of thread, and then I've modified a set of glass pipettes, so they'll serve as little hooks that we can work with. And so now right here, we can start to see the nerve. It's usually a little bit yellowish in color and pretty distinct. And they are actually contacting it with metal scissors in this video, but we want to avoid that. So you'll notice here they've got a little hook to just separate out the nerve as they're continuing to work and work it free. So what they're doing now is taking a piece of thread and looping it around the end of the gastrocnemius. So the end of the gastrocnemius is the Achilles tendon, and this is going to be the point that we will attach to the force transducer. So you want this to be a very secure knot. They illustrate a looser knot here, but you'll want this to be a square knot, right over left and left over right. Good and secure so that it doesn't slip free in your preparation. So now they're just going to cut the tendon below where that knot has been tied to free the muscle. Okay, now the muscle is free. And the gastrocnemius, its origin, so the other attachment point for the muscle, is actually along the femur up here. You have two different options for securing the femur end of your muscle. So one of your options is just to use a couple of dissecting pins, stick them into the quadriceps muscle here, and secure your femur in place in the dissecting pan. The alternative would be to free the femur, so you need to cut the femur with a set of bone shears, also free enough of the nerve that you can bring the nerve along with you, and put the femur into a clamp. The advantage of the clamping method is that you will want to be able to measure the length of your gastrocnemius at different points. And if it's in the clamp, you have a shorter distance to measure and less material wiggling around. On the other hand, it can be faster to use the pin method. You just will have a much more challenging time measuring some of the distances later on in the lab. So the last thing is in this video on the hooks that are illustrated here are actually part of a stimulating probe used in this particular preparation. So our probes are shaped a little bit differently, but this shows you how to arrange the probes if you are to provide an indirect stimulus to the muscle. So the indirect stimulus is to stimulate the muscle via the nerve compared to a direct stimulus where you would stimulate the muscle tissue directly. Okay, and now that you've had a chance to see how that muscle is prepared, the other component of lab is going to involve setting up Power Lab lab chart to measure some of the outcomes of what we're doing. And along with that, I need to introduce you to the method that we're going to use to stimulate the muscle to contract. So we're going to start with kind of an overview of the instrumentation, and then I'll switch over to some of the details of the lab setup. So for this lab, we are going to use a stimulating unit shown here called the GRASS stimulator. And I have this set up already, but I'm going to take it apart again. So this stimulator is it's pretty old school, but it's fantastic. It's designed really well to allow us precise control over the stimulus that we give to the muscle. So the way it's set up, we've got this set of these 4 switches down here, and then a set of 4 dials here. Those correspond to 4 different aspects of the stimulus that we can deliver. So we've got the frequency, how many, delay, so delay before the stimulus is delivered, the duration of the stimulus. I should say the delay is also delay between stimuli, duration of the stimulus, and then the stimulus intensity by voltage. So for delivering our stimuli, you're going to use a stimulator that looks something like this. And it may have either 2 or 3 wires coming out of it, so you're going to have a positive, negative, and potentially also a ground. This particular stimulator suffered some abuse 2 years ago, so the ground connection is missing. And there's actually a couple different ways that we can plug into the stimulus. And in this case, what we're going to do is these knobs will unscrew. They'll expose a metal section, so we're just going to contact metal to metal to connect everything up. So I'm going to lay that in, then I'm going to tighten this down to hold things in place for both the positive and the negative. In this case, so I don't need a ground necessarily. We're not going to be working with insane voltages, so that's not a really big deal. And then we've got a couple other toggle switches down here. So this was initially off. You do want to turn it on. And you want to make sure that your output is set to mono, and we're going to stick with regular stimulus here. And you can actually change the polarity of the stimulus to normal or opposite, kind of depending on your interest. So pretty versatile. So that's for delivering our stimulus to the muscle or to the nerve. And then, of course, we need to measure the response of the muscle to the stimuli that we deliver. So our old friend, the force transducer, is going to come back into play. Again, we're most likely just going to use that on the lowest possible setting. You're going to want to hook that up again into your ring stand, into the adjustable ring stand. And you're going to want to follow the same calibration procedures as before. So pull out your calibration weights, use the 2 gram and the 10 gram weights to calibrate your force transducer, and then that will be set up and ready to go to measure force production. Along with that, we also want to measure the voltage traveling across the muscle. And so for doing that, we're going to use a set of needle electrodes. And we actually have sets of 3, so I have positive, negative, and ground. So these are pointy, don't stab yourself. You're going to stab the muscle with them eventually. And then, so for the ground, you don't actually need to do much with the ground. You can just kind of leave it. And then for the other end of these are going to then get plugged into input number 1 using the same adapter we used for the Ussing lab. Just make sure that you realize here that green is ground, so plug in the green where appropriate. As another reminder, I have the Power Lab up and running here. The sequence you want to follow for the Power Lab is to start out with nothing plugged in, turn the Power Lab on, wait till you get the ready light, then plug in your instruments. Once you've got that done, then you're going to fire up chart and you're ready to get underway. Once you've got everything hooked up, you're now going to want to test everything and just make sure that your stimulator works, that your recording electrodes will record. So what I've done here is I've taken this stimulator and then I've taken my 2 needle electrodes here, those are my recording electrodes, and I've just connected them with each other for testing purposes. And you may wind up having to fiddle around a little bit with this configuration to get everything in contact with each other. But then I'm ready to start doing some testing. So I've loaded up lab chart, and I'm just going to start running that in the background here. Okay, and at the moment, for my starting conditions, what I have right now, so this lower set of knobs is a multiplication factor. So I can either go in a range that's in the 0.1 range, in the 1 range, or in the 10 range. So at the moment, I've just left frequency in the 1 range, and I've left this knob down at a frequency of 2. Also at the moment for delay, I've got that at in the 1 range, and I have 0 delay. For duration at the moment, I want to be somewhere between 2 and 4 milliseconds. So again, this is at the ×1 multiplier, dial in between 2 and 4. And then for my starting voltage, I'm going to start with starting voltage of 1. So now I've got chart running. I've got my initial conditions set where I want them. So to just do a single test, I'm going to use this mode toggle switch here. And if I press down once, that will deliver a single stimulus. Okay, and it's not showing me anything on chart. So what that suggests to me is that I might have a contact that's not complete at the moment. So, and as you can see, there's some background voltage here, even when I'm not delivering a stimulus. So now I'm going to try repeating that. And hopefully what you can see is I'm detecting a voltage with the electrode. So every time I press this, when I have good contact, and I've lost good contact. So again, it's a little bit finicky, but if I have good contact, anytime I stimulate, I detect the voltage that I have stimulated at. You may have to do some troubleshooting at this step. So for example, it might be that you have 3 wires and you haven't figured out your stimulating wires versus your ground. And as you just observed, there might be some issues with the contact between the stimulating electrode and the recording needles. But once you've satisfied yourself that the stimulating electrode does indeed deliver a stimulus and that your recording needle electrodes will record the voltage, then you're ready to apply the needle electrodes to the gastrocnemius, and you want to spread those out at either end of the gastrocnemius. And then when the time comes, you'll be ready to use the stimulating electrodes to deliver different stimuli. Just a couple other notes. You are going to need to read through the setup instructions very carefully and follow them closely. And in the initial stage, as you're preparing everything, you're going to be running some tests to figure out the muscle threshold voltage. So just kind of as a baseline, it's a good idea to just start with all of these in the 1 range and start with your voltage at 1. So now it's time to talk a little bit about the sub-experiments that we're going to be conducting. The first one is just going to be determining the threshold voltage below which you do not see any muscle contraction. So you're going to start out at some particular voltage where you see a contraction, then step down from that voltage in increments of 0.1 volts until you reach a voltage where you do not see any force produced in your force recording channel. From there, then you're going to determine the maximum twitch tension. So for that, you're going to start gradually increasing the stimulus intensity. And keep in mind across all of this, you're working with a muscle. If it were your muscle and your muscle got stimulated non-stop for an extended period of time, you'd start to experience some fatigue. So you don't want to rush your way through these procedures. You want to allow some recovery time in between each stimulus. So just follow the directions for your maximum twitch tension. After that, what you're going to do is determine the optimal length for contraction. So that is going to involve adjusting the height of this height adjuster and measuring the distance, change in distance between this and a fixed point on your muscle. So typically where the femur is located on the muscle. Okay, from that point, then you're going to switch your recording, and in this case, what you're going to do is you're going to adjust the sampling rate. So for doing that, I'm going to stop the recording I have going currently, and I'm going to go up to the setup window, and I'm going to select channel settings, and this is going to bring up some setup conditions across the different channels. You'll notice one that is a drop-down menu for the sampling rate. And so for this, what you're going to select is 10,000 samples per second. And that's going to change across all of your recording channels. So then if you click OK, what you're going to notice is now your sampling rate is a lot higher across those channels. That's critically important for being able to capture very fast events. And this also highlights why you need to write down your calibration settings, because you're going to need to recalibrate in this new file. From there, you're then going to examine how temperature impacts muscle contraction properties. And past that point, we'll start examining stimulus frequency. So there we're going to start adjusting some other aspects of our settings on the stimulator. So there's a range of conditions to evaluate for looking at the effects of the stimulus frequency on contraction patterns. After that, we're going to switch from direct stimulation of the muscle, where we're applying our stimulator to the muscle, to evaluating the impacts of indirect stimulation. So for this, you're going to drape the nerve across the stimulator and instead stimulate the muscle through that route and examine the same properties as for the directly stimulated muscle. And then past that point, the last thing you're going to do is evaluate the length-tension relationship. So you're going to put everything back to the settings that produce the maximum twitch response. You're going to note the length of the muscle. Then you're going to stimulate at that length. Then you are going to decrease the length of the muscle, so shorten the transducer, and then stimulate again and record the tension at that new length. Then you're going to come back to your starting height, then raise the transducer so that it's higher, so the muscle is longer, and then you'll stimulate once again. And you're going to want to increase to a point where the contractile response is obviously smaller than your initial contraction. Then for this lab, I've left a section in for the data summary. So I do want you to develop a data summary. You'll notice a lot of that is going to involve getting screenshots of different muscle stimulus measurements. So budget some time towards the end of lab to collect the screenshots that you need for that data summary.